right, good morning everyone. I want to welcome you to the tutorial. We here have Rohit Bothra from Brocade Communications, who's going to talk about the pros and cons of large-scale route reflector deployments. So thank you very much.
A very good morning everyone. Thanks for joining me this morning. My name is Rohit. I work as a staff QA engineer for Brocade. So today's topic we are going to discuss is demystifying the pros and cons of large-scale route reflector deployments. So first, as part of the objective, we would like to go through what are the options available for the ISPs for large-scale deployments of internal BGP. Then we'll walk through what are the deployment models for route reflectors and what are the advantages for each of those deployment model. And we also would like to discuss some of the pros and cons of large-scale RR deployments. So as we all know that when it comes to the inter-domain routing, BGP is the de facto protocol which is widely used across the internet. And specifically for the large ISPs, when they deploy BGP to their internal core routers, so the challenges they face is of scaling. So once you have a very large setup of BGP deployment, so obviously the challenges are how you can scale well your protocol, because at the end of the day, all of your services depends on how you actually deploy your BGP. So the complexity again increases when you have different kind of services. So if you look at large ISPs, the challenges they face is once they deploy new services, they have to think about their internal routing scalabilities and reliabilities. So what you are going to do is that there are three options for BGP large-scale deployments. We want to discuss all three and specifically focusing on the route reflectors. And some of the challenges or some of the disadvantages we are often not discussed, which are related to route reflectors. So first, we just go through some of the basics of BGP. So what is it, and what are the main type of sessions which is related to BGP? So as you see in the picture, we basically have eBGP, iBGP, and IGP, which actually made the core of any large-scale ISP. So the role of iBGP peering is basically to exchange the external routes from different autonomous systems into your own autonomous system. The role of iBGP, as you see, is marked as green, is basically runs internal to your network, which is responsible to carry your customer prefixes and partner prefixes throughout your network. And underlying your core network is basically your IGP, which is responsible to transport the next hop of your BGP routers, BGP peers. So you see basically the R1, R2, and R3 here denotes the next hops. Once you have eBGP sessions, your prefixes will be delegated by your AS to your internal AS, and then those are actually passed through your iBGP to your internal devices. So that's how you basically reach out to all the prefixes inside or outside the domain. So this is the forwarding path. Once you have the control path ready, then you basically reach out to those prefixes which are advertised across the interdomain ASs. So this is in summary basically why you need eBGP. eBGP is basically you learn your prefixes from your neighbors. iBGP is for your internal communication. You delegate those routes to your internal core network, and IGP is basically the glue which ties the, which provides you the path for the BGP next hop prefixes. Next hop. So now comes the challenges, right? When you have a large scale deployments, you end up having thousands of BGP speakers. Now, the rule of iBGP says that your internal iBGP, one iBGP prefix peers cannot advertise the prefixes to another iBGP. That's basically the loop prevention in BGP. So that's the reason we need to have full mesh of all BGP speakers inside your network. So that brings the challenges of scalability. So what happens when you have, let's say, tens of thousands of devices? If you want to scale those number of sessions, it will be nightmare for you to scale up and maintain those devices. So this is one example where you see there are only 4 nodes which are connected full mesh. So why we need the point-to-point connection inside the iBGP? Because as I said, the loop prevention mechanism in BGP is such that the internal iBGP doesn't carry the AS path. So that's why you need to have the full mesh connectivity between all your internal peers. So let's see, this is a typical example of 3 cities. Let's consider where I have POP, if I am a large ISP. And if I want to deploy full mesh of BGP, just imagine I need to run my logical sessions across different routers inside my POP, and this will not scale up very much. So this is just example how I can calculate the number of iBGP required if I need to do everything in full mesh. Just imagine if I have a number of 1,000 routers. So the formula is n into n minus 1 by 2. That much of peering sessions I need to bring up to make sure all my BGP inside my core are connected. So that's huge. So what are the solutions which we often talk about is your Route Reflector and Confederation. There's another one which is basically BGP free core, which is mostly used when you are using MPLS as your core. So basically what you do, you don't need to run iBGP session inside your network. You just run MPLS that will act as a transport, and then on the edge you basically run your MPBGP. So what are the scaling limits? Why we were worrying about so many scale numbers? Why we are worrying about scale? The reason is because if you see the router density is getting increased day by day, more and more routers are now added up to the large scale BGP core. Once you have number of routers increased, you basically, for each additional router, you need to run, let's say, those many number of sessions with existing routers. So this definitely brings the challenge of TCP scaling. And also, in full mesh case, what happens, each update is actually processed and delegated by each and every router. So in that case, you just imagine the bandwidth required for processing the updates. And also, we know that in most of the BGP implementation, you basically maintain 3 routing tables, which is RIB in, RIB, and RIB out. So RIB in, basically, you have the unprocessed BGP updates. RIB is basically your processed updates, and then whatever updates you want to send to your peers. So these are the limiting challenges which we need to address when we talk about iBGP. And additionally, you also have configuration challenges, provisional challenges, because once you add a new router, you need to make sure that this router has pairing with every other router in your core. So I'll just quickly go over what is BGP Confederation, what is the idea behind BGP Confederation, and then later we'll focus more on route reflectors. So the idea behind Confederation is divide and conquer. Basically, you take your autonomous system as one, and then you divide this autonomous system into logical sub-autonomous systems. So basically what you are eventually achieving is you cluster your routers in small autonomous systems inside your own AS. So basically, what you are achieving is, inside that small autonomous system, you can have full mesh of iBGP. You need not to worry about the other routers in other autonomous system. So logically, if you think, your internal autonomous systems, the sub-AS becomes your iBGP, and then the other autonomous system becomes your neighboring autonomous system, neighboring AS, which becomes your eBGP session. So eventually what is happening, we call it as iEBGP, because even though it is your own autonomous system, you are logically breaking up these systems into small autonomous systems. So this is well described in RFC 5065 in detail. So usually what happens, you need to run a single IGP across your autonomous system. So these are actually again for reachability of your next hops. So in case of configuration, what happens for the outside actual autonomous system, it is again visible as a single AS. Your logical sub-ASs will not be visible to the outside world. And what you basically do is, when you have your small sub-ASs, you run the private ASs on those sub-ASs. Now, in case of configuration as well, when you have sub-ASs, you need to run full mesh of iBGP. So if you need to take care of the size of your sub-ASs, because if it is too big, you need to again think of running route reflectors inside your configuration sub-ASs as well. So this is one example where you see you have AS200, which is logically divided into 3 sub-ASs, 655303132, and this is just a sample configuration where you need to assign the identifier, which is your actual AS, which will be visible to outside world, and you have your sub-ASs which you assigned, which are private ASs, to your sub-AS inside your own AS. So one of the important thing to note in configuration is that basically it preserves your next hop local preference and met properties. So that's why it is called as iEBGP. So even between the sub-ASs, it runs logical eBGP, but it will preserve your BGP attributes and properties. So basically, these are the fundamental principles which drive the configuration. So what benefits we derive out of configuration is basically it solves your iBGP full mesh problem. Your packet forwarding is not affected because it takes care of it, and it can be actually used with route reflectors as well. But there are certain challenges when you deploy with configurations. The most important challenge is basically the AS sub-hierarchy. So as we discussed, right, that once you have your own AS, you can actually break into sub-ASs. Now you cannot further breaks those sub-ASs into further sub-ASs. This is not possible in configuration. So basically, you cannot have hierarchical ASs in configuration. Other problem which it introduces the part diversity, which we discuss more in detail. What is it and how it avoids. And the most important challenge with configuration is migration. So basically, in case of route reflectors, you can have incremental deployments. But in case of configuration, you have to think about your entire AS and deploy it at once. You can't have incremental deployments in case of configuration. Now let's move to route reflectors. So again, your route reflectors solve your problem of full mesh, but in a different way what we discussed in case of configuration. So the idea behind route reflector is that all your updates will be processed by your Route Reflector, and then those processed updates will be sent over to the Route Reflector clients. So in this picture, if you see, right, we have 4 clients: client 1, client 2, client 3, client 4, and in between we have a Route Reflector. So what it does, basically you receive a prefix from your peering AS. This will be received by the Route Reflector. It will be processed and delegated to each and every client. So now think how the problem is getting solved. So earlier, if we have one prefix which is received by the internal iBGP members who are in full mesh, we need to run n into n-1 by 2 sessions. But now what we are doing is we have a single RR which is running iBGP with its clients. So client to client iBGP session is not required. And if you need to add any other client or any other router inside your core, you just need to bring up the peering with your route reflectors. So it's just a single increment. So basically this is how your route reflector does processing. What it does, basically it receives the updates from peers, and then it will delegate those updates to your other peers. So essentially, in case of full mesh, the received iBGP updates were not able to send to other iBGP peers because that's how the BGP works. But in case of route reflectors, it relaxed that rule and is basically send those updates to other peers as well, basically client. And it basically, you can imagine this as provider, peer, and customer kind of concept where your updates are processed by route reflector, and then those are actually delegated to other clients and non-clients. So the golden rule of route reflector is, if I have a peering with eBGP, or if I learn eBGP routes, I will forward to all my clients and non-clients. If I have routes which are learned from my clients, I will reflect to my clients and non-clients. And if I have routes which are received from non-clients, I will reflect only to my clients. So this basically comes into your control path. Route reflectors need not to be in your data paths necessarily. This is one example with a single route reflector deployment where you basically have a route reflector R1, R2, R3, R4, your next hops, and let's say you learn some prefix over those next hops. So over the iBGP with client, route reflectors will learn about those prefix. It will run its own best path selection algorithm and then finally delegate the best route to your internal peers. So one thing to note is that even in case of route reflectors, we delegate only the best path. And this is your forwarding path once you learn the prefix. Now look at the typical scenario for a large ISP. So in case of large ISP, you basically have your POPs, you have your regional core, and you have your super core. So while deploying route reflectors, what normally the providers does is basically you have at the POP level you will have certain route reflectors. Let's say per POP I can have 1 or 2 route reflectors, and those route reflectors will be client to my regional core, and those finally will be client to my core, super core. So, and one important thing to observe is that when you have a RR deployment, you need to run full mesh between the RRs. So basically, if let's say the green routers, you can imagine as it route reflectors for the POP, and the blue one you can imagine as route reflector the core. So basically, those has to be paired in full mesh. So what are the advantages related to route reflectors? So the most important is related to scalability. So now, as we see, when you have full mesh of BGP, you need to run iBGP everywhere, and if you add a certain router, even one router, you need to again bring up the peering with all the other routers inside your core. So what happens with route reflectors, you need not to worry about pairing with other clients. You just need to bring the pairing with your client, with the route reflector itself. That's enough. And second important for your control perspective is your the way the updates are getting processed. What happens, basically your updates are not sent across all the routers. Your route reflectors will be processing all the updates, and then those updates, whatever is the best prefix, will be delegated to the other clients. So other advantages from the control perspective is you now have smaller BGP routing tables for your clients, because it is not running in full mesh and it doesn't need to process all the updates. From the deployment perspective, again, from provisioning side as well, you have less overhead of configuring route reflectors, because clients are not even aware of having a route reflector into your system. You just need to put the configuration part only on route reflector itself. And this saves lots of dollars for you. So far, what we discussed is the challenges of iBGP full mesh, the solutions, confederation, and route reflectors. Now let's look at some of the challenges which comes with RR deployment. So what are those challenges? The most important, I have just mentioned two, is part diversity and convergence. So what is part diversity? So you think about a large ISP. It will have customers, it will have peers, it will have the exchange points. So with large scale ISPs, you have different kind of prefixes coming to your inside network. It may be of your customers, it may be of your peers, or it may be at the exchange point. So once you have very large number of prefixes, right? And just think about the internet. The unique prefixes size has crossed over 400K, and total number of routes has crossed more than 4 million to 5 million. So with those many routes, if you have to have inside your core, you need to think about different prospects while deploying the route reflector. So part diversity can be of three types. It can be part diversity of your prefixes at the POP level, part diversity of your prefixes at the RR level, which concerns about the next stops, or it can also be at the AS level. So the major advantages of having a very high part diversity is that basically you have alternate routes to reach those prefixes inside your network. So once you have alternate routes, you can actually better program your inside traffic engineering, you can better load balance, you can also have ECMP. So those are the advantages of having large part diversity. Now think about RR. When I deploy RR, what it basically does is it takes all the paths from, it learns all the updates from clients or non-clients. It processes those updates and then finally send a single best path. So what about the other paths? It basically gets hid behind the RR. So in case of convergence, what happens when you lost the primary path? You need to find out the alternate paths. So those paths gets visible once you have lost your primary path inside behind the RR. So the intention is once you have large scale RR deployments, so existing part diversity has to be checked. Basically, you need to worry about what is my part diversity at the next hop level, at the POP level, and at the AS level. Because this will give you an advantage of characterizing the properties of your prefixes. It will give an advantage of quantifying those prefixes. It also gives you an advantage of better understanding your internal routes and your own network. So the other disadvantages which comes is the convergence, which is very important when we talk about any BGP deployment. So convergence in a very simple term is the state at which all my routers are in sync. It can be of two types. It can be a convergence up event or convergence down event. So normally the convergence up events are related to when I have certain changes inside my network. Let's say if I add another peer, or if I have another link added to my network. Convergence down events can be triggered whether your links inside your network going down or some routes are getting flapped, those kind of events. So the idea is basically you characterize the convergence as well. So the major important characters of convergence is your number of updates, because this essentially relates to your processing time. The internal events, which can be your link flaps, route flaps, IGP flaps, next of change, those kind of events. And of course, the overall time which you want to measure inside your network related to convergence. So other challenges which also comes with large scale route reflector is data forwarding loop or control loop. So we'll go through how exactly it happens. So this is one example where we can see how the part diversity gets reduced because of RR. So initially we have all the routers in full mesh. So all these routers are connected using iBGP. When I learn some prefix, all prefixes are actually sent over all the peers. So all my peers are actually seeing those routes. So the path is actually visible. So you see I have both the path information. Now let's replace the full mesh iBGP with RR. So now these are my clients and I have a RR in between. So what happens, I learn the routes. The routes will come to my RR. RR will process those routes and send only the best one. So now what happens for the other routers? Let's say in case of router 3, it will have only single path. The other reason for path diversity reduction can be related to the BGP attribute itself. So we know that BGP runs a best path algorithm depending on certain attributes. It processes those attributes and then finally come up with the best path. So the first four, local preference, AH path, origin and mid, are actually considered as the topological independent parameters, which not necessarily depends on any topology of BGP. The other three, which is eBGP over iBGP, IGP cost or router ID, they are actually related to how you place your router inside your BGP topology. So they are also contribute to the part diversity of your prefixes. So what essentially we need to do is basically we have to think about the deployment, from the deployment perspective, how I can actually characterize my part diversity, whether the existing prefixes are actually not hidden by my policy, which is BGP best path selection algorithm attributes, or it is because of my route reflector deployments. So this is one example of delay of convergence due to route reflector. So what happens when you have the full mesh of iBGP? Once your AS prefix is gone, the withdraw message will be received by all the routers at once. So there's no additional hop which needs to be traversed here. But when I put RR, right, and normally in case of RR deployments, we deploy RR in number of 2. So the second RR will be for redundancy purpose. Now what happens, you have these update paths available. So the additional delay is because of the RR deployment now, because once you have iBGP full mesh, you are not having any additional hop once you receive the prefix. But in case of RR, you have additional hop which is introduced by the RR. So once your prefix goes down, the withdraw message which be received by the RR, those are processed. And if it is not sent to the clients, let's say there are some processing delays, then the end client will actually explore the other paths before declaring the prefix to be down. So this is one example where your other paths are still available even though the path is actually not there. So this is the second alternate path, and this is the third alternate path. So finally the client will sense that the prefix is not reachable. So fundamentally there are two types of delay introduced because of RR deployments. One is due to the hierarchy, which introduces the additional hop, and other because of the redundancy. Because once you have redundant RR deployment, those redundant RR will also generate the updates, and those has to be processed by the clients before coming to a convergence point. So this is basically how your convergence can be delayed because of your RR deployment. So these 2 points just we discussed, right? If you have the redundant RR and if you have hierarchical RR, both introduces additional hops inside your network. So the prefixes which has to be processed by the RR and then finally by the client. So there's additional delay. The other problem which is well known is actually very well defined in RFC 3345. So what happens when your route reflector topology doesn't follow your physical topology? You may end up in creating forwarding loops. So this is from the data plane perspective. So in this simple example, you have two RR which are shown in green, and you have two clients. Now think the clients are actually not following the physical topology. So my left-hand side client is actually a client, left-hand router is actually a client of RR2, whereas my right-hand router is actually a client of RR1. So what happens for the best path of the same prefix for me? So now in this case, the RR is actually in the forwarding path as well. So for the left router, when I want to reach that outside prefix, I will prefer the path from R1, but I will go to the next stop as the right side. So now what happens for the right hand side router? To reach the same prefix, it has to go to the left hand side router because their physical and logical control topology are not same. So what happens essentially, they end up sending the sending the data to each other. So in that case, it can create your routing loop in the forwarding plane. Another example is at the control plane, a problem at the control plane, your route oscillation problem. So what happens when you have RR deployments? As I said earlier, that when you have RR deployments, you need to have full mesh of iBGP among the RR itself. So in such scenario, when you have the path preference of BGP, right, which is the first four is topological independent and the other three are topological dependent, and you just keep it everything same, what happens? Because of two main BGP attributes, which is mid and the IGP cost, your route will be withdrawn and updated by the route reflector deployment. So in this case, what happens? Let's say RR1 prefers R2 over R1, and then for the RR2, what happens? It prefers the R3 over R2, and for R3 it will prefer R3 and R over R3. So this is basically cyclic. What happens? Those updates will be first processed by individual route reflectors, then sent across to other. So those updates which are received by the other route reflectors, if the withdraw message is not received at the same point, then the best path algorithm will kick in, and then each individual RL will decide or choose the path which will oscillate at the end. So this will keep happening in a cycle. So far we discussed about different aspects of route reflectors and what are the problems which are very important for us to understand, primarily the path diversity and convergence. So here are certain solutions which can be deployed with RR deployments. So these solutions are not necessarily available with each vendors. These are certain solutions which are already available in the market with many vendors, and certain solutions are still under research. So one of the important thing is to understand that when you deploy route reflectors, your control topology is dependent on your physical topology. So you should always have your route reflectors, or the clients should follow the physical topology. So essentially you should have your clients as close as possible to your route reflectors. And you need to make sure consistency. So basically what you have to do is your forwarding path and your control path should follow the same RR. And third is basically high degree of replication, which brings basically how you deploy route reflectors inside your POP. It can be as pair of two. It can be in hierarchical as well. So this is again possible solution. This is not as of now is available for with vendors. So what happens? Let's say you learn different prefixes having different next hops, same prefix. So the green router is basically the route reflector. So as of now, if I receive multiple routes, what I will do, I will run the best path algorithm and then finally send only the single best path to my client. So in this case, what can be done is basically you receive all the routes and then you basically send all those routes to your clients. Now the client will decide which one is nearest to me, and then I will choose that as my exit point. So what happens? Basically you make your route reflector more porous. In that case, you expect the route reflector to send all the prefixes and then let the client decide which one it wants to choose as the exit point. But essentially the disadvantage associated with this kind of deployment is that basically you need to have more updates to be processed now from the client perspective. Another way of solving this problem can be customization of dissemination, because what you do is you get the routes from route reflector and then you send customized routes to your clients. So that again not necessarily the best route. So basically the advantage is it looks like you are actually deploying the routers in a full mesh, because all the paths are now visible to you as a client. But the disadvantages associated with this kind of deployment is that your RR has to be very intelligent, because you are customizing on the fly. It's basically real time. So other possible solution can be tunneling across the routers. So this is actually used today in MPLS deployments. What you have to do is basically you form logical tunnels and then you send your updates over the tunnel. In that case, you basically avoid processing time, and you will basically receive all the updates over the tunnel. But the disadvantage associated with such kind of deployment is basically again you run up with the tunnel full mesh, so which again will bring up our scalability problem. So in summary, basically when your full mesh doesn't scale, what you have to do is basically you need to deploy the route reflectors. Again, it depends on how you want to plan. You can have pairs of route reflectors per POP. You can have your regional route reflectors, and then you can have route reflectors at the core. So these are the recent ideas what we discussed are available, and certain ideas are actually getting productized as well. So other things which I would like to share is basically when you have the RR deployments, you also need to worry about certain design, which is basically how you want to design your route reflectors. It can be in hierarchy or in a pair of two. Other thing is that when you have RR deployments, you introduce two non-transitive attributes, which is basically your cluster ID and originator ID. So basically, cluster ID is how I can prevent loops when I have RR deployments. In certain deployments, it is observed that it is better to have route reflectors, a single route reflector inside a single cluster. In certain cases, it is also advisable to have pair of routers in single cluster. So the advantage with different cluster is basically you need not to you have more path diversity, and when you have route reflectors inside single cluster, you will have less path diversity. So far we discussed that what are the things we need to keep in mind when we deploy route reflectors. From the industry perspective, there are different solutions which can be deployed with RR. So these are not like specific to any particular vendor as such. So what I did is I noted down all the solutions which are currently available in the market across different vendors. So BGP pick or add path are helpful in your forwarding plane. What happens, as we discussed, when you have any BGP deployments, BGP actually sends the only best path to other clients or peers. So with BGP pick, basically you have two solutions in the core and in the edge. So when your core link goes down or your edge goes down, you have redundant path available at your forwarding. So your forwarding is not impacted. Same as add path, when you deploy essentially with route reflectors, what you can have, you can actually ask route reflectors to send more than one best path. Virtual router is again deployed as a shadow router. So basically you have a primary router and then secondary router. So primary router will always send you the best path, and the secondary will actually send you the second best path. BGP multipath again is very useful in case of load balancing. So what essentially you have different paths to reach the same destination. BGP best external again is used mainly for backup purpose. What happens at the edge when you receive the external prefixes, and your external prefixes are actually sent by your edge, whatever is the best, because what happens when you have at the edge, you will apply the BGP policies, and because of that, as we discussed earlier, your path diversity will be reduced. But with BGP best external, what your second edge or the backup edge, what it does is basically it can also send the second best or alternate external path to your internal iBGPs. VPN unique RD, this is actually deployed for route reflectors in MPLS core. So what essentially does, normally we assign the router ID or RD value to each customer to distinguish the customers. But in this case, what you can do is basically for different customer sites, you can assign different router IDs or RDs values. So when it comes to your route reflector, it will consider those routes as unique because each of these routes are assigned with different RD value. So by this, what essentially you can do, you can actually reflect both the routes to your inside peers. And last one is multiple cluster IDs. So basically when you deploy RR, you essentially need not to have the peering among the clients itself. So as we discussed, once you have RR deployments, you should have the peerings between your route reflector and the clients. But in certain cases, in certain deployments, it is observed that you also need to have the client-to-client peering as well required. So in those kind of scenarios, what you can do, this feature is very useful. You basically assign each neighbor, each client into a different cluster ID, and then in your in your route reflector, you basically can have configuration to avoid the client-to-client reflections. So let's say if I have a client A and client B, and I put those clients into single cluster, now I can have policy which says that okay, you reflect all the routes from client A to client B, or you don't want to reflect those routes from client A to client B. So those kind of policies can be very well deployed with this kind of solutions. So in summary, basically what we discussed is as your network grow and you have route reflector deployments, you need to think about how can you actually characterize, quantify the important parameters which affects your forwarding. So if it affects your forwarding, it will essentially affects your services as well. So there are different techniques which are available in the market. You just need to think about which technique or which solution fits your requirement, and then actually you can basically have certain parameters which you need to tick and then deploy those kind of solutions. So what happens in case of route reflectors, for all the monitoring purpose, normally the ISPs runs the passive session with your route reflector. So from those you will get all the prefix information, and once you have prefix information, you can actually quantify and characterize. Just to give an example, basically let's say if I am a large ISP and I'm worrying about how many percentage of my prefixes are actually having part diversity from, let's say, range 5 to 9, which is considered as a good part diversity. So what I need to do, I need to first find out, or first I need to run passive monitoring with my route reflectors, get all the data, and then quantify those data. So one of the observation is seen that for ISPs which doesn't have geographical presence in one location, those turns out to be having large part diversity. The reason being those clients or those peers doesn't have direct connectivity with the ISP itself, so it has to go through some other ISPs or some other regional ISPs. So the prefixes will have very high part diversity. So in this case, basically your autonomous system part diversity will be very high. So in these cases, the part diversity can run from 40 to 50, so which is too high, again not desirable. So those kind of things has to be quantified, has to be understand well before we get into deployment. Same thing from the convergence perspective. What happens if you have a RR topology which is not essentially designed well, which is not following your physical topology? So the major disadvantage which will be faced is your data forwarding loop or your route oscillation, which we discussed earlier. So those kind of things has to be keep in mind. And the last but not the least, from the policy perspective, again, as we see, we can actually characterize the attributes also. So the first 4 attributes are not dependent on topology, the other 3 are. So with all this in mind, once you have your internal core running BGP with the route reflectors, you will basically get better result, you will get benefit, and end of the day, you will have better customer satisfaction. So this is all I have. Now if you have any question.
Hey, this is Karthik from Affirm Networks. Question for you is, given the state of the standards right now, is route reflection with multipath completely viable to implement so that you can avoid all the, the looping and all the stuff that you pointed out?
Yeah.
It is.
Yeah, it's a good question. Basically, definitely it is viable with route reflectors. So only thing is, again, you have to worry about your policy design, as I discussed. So for multipath to be very deployable solution with RRs, you need to worry about the other path vectors. So basically, let's say you need to come at a point where you can receive the different updates for the same prefix and then make sure that your topological independent parameters are same. So in that way, you can actually deploy those solutions with route reflectors as well.
Comment question on your slide 41, vendor solutions.
Okay.
Great slide. The slide says vendor solutions, although many of those solutions are in RFCs. My question was, are all of them in RFCs? And I'm not sure about BGP PIC. I know Cisco BGP PIC, but
yeah. So if you see BGP PIC is actually available.
It is an RFC. So yeah.
There's no RFC.
Okay, so
there's no RFC.
So I guess my basic question was, which one of those are not RFCs? Because many of them are.
Yeah, so not sure exactly, because what I did, I just tried to find out all the available solutions as such. So I didn't.
AdPath for sure, multipath for sure.
Yeah. So I think multipath is definitely RFCs there. For BGP external also, I think there's RFC.
I think everything except BGP PIC is a standard, or BGP PIC and virtual RR. Virtual RR is just a way of implementation, right? So on the virtual node, not on the real router, which is different story. And BGP PIC is how the internally in the software running on the router, the BGP next hop are resolved by internal path or tunnels.
Yeah.
So it's internal behavior of the.
I agree. PIC is really internal. It's not signal.
So
it's not a point to standardize it.
Yeah. So let me explain how it works. So think BGP PIC. Let's say you receive thousands of prefixes, right? So when you receive those prefixes, you basically translate those RIB entries into your FIB entries, forwarding entries, right? So in forwarding entries, basically what you need is your next hop, resolved next hop, because your next hop can be recursive, and then you finally find out the exit point, so the exit interface. In normal flat FIB architecture, what happens? Your next hop interface and next hop exit interface are tied up. So let's say there is any change in next hop, all your 1000 prefixes has to be updated in your FIB. But in case of PIC, which is a different design, it's a hierarchical design. So what essentially it does, when your next hop gets changed, only the IGP is getting impacted. So from the BGP perspective, there's not that much update has to be done. So in that way, it's basically very useful.
No, I agree. There's no signaling for PIC. It's no different than FRR or LFA.
Yeah, so it's basically a forwarding solution.
It's internal to the node.
Yeah.
But okay, most of them. I was just not familiar with 2 or 3 of them, so they are in RFCs. Okay.
Sure.
Hi, Clinton would tell us. I just had a question. You didn't really cover it here. Are there pros and cons people should consider in their design, whether they use external route reflectors or actually implement the route reflection on their existing routers? Thank you.
Okay. Can you repeat your question?
I'm just wondering if there are design considerations about using, implementing route reflection on the actual your existing core routers, or going with dedicated route reflectors.
Okay. So essentially, there are 2 parts as I discussed, right? If you, let's say, already have an existing route reflector deployed, right? So you need to characterize from the perspective of your path diversity and convergence if it is already existing. Because what happens if you, let's say, your design is varying. At the POP level, let's say you deployed RR in a pair of 2, but at the regional core, let's say you have only a single redundant. So what essentially you are doing is you are having a problem of scalability and as well as reliability. So those aspects, if you are already deployed, has to be characterized, and then you need to take a decision whether you want to change those existing designs. And other things, what you said, if you are having a new deployment, then I would suggest you need to design your physical topology in such way that it actually, when you deploy RR, it follows the physical topology. So for example, you are coming up with a new POP design, and let's say you know what is the size of my POP, right? If the 2 route reflectors are sufficient, you go ahead and deploy that. If you think, right, you need to put those reflectors into certain, again, depending on your POP requirements. So what you can do, you can actually put single or both the route reflectors into a single cluster, or you can have both the routers into different clusters. The reason being said is all this boils down to your convergence and part diversity. So once you have, let's say, single router, right, or dual routers which are deployed as a pair, so the other pair which is redundant will also generate a lot of updates, and that has to be processed by the clients, and which has an impact on the convergence as well.
Okay, thank you.
Good morning, Don Lasher, F5. 2 notes real quick. On the tuning section, 2 things that can really help from a convergence standpoint is advertisement interval and adjustment interval, or update interval.
Right.
Depending on the version of the iOS, depending on the hardware platform, update interval in some cases can be by default a lot higher and can be reduced to something like 0.
Right. Yeah, so just to elaborate, it's a very good point. When you have convergence-related parameters, there are 2 important factors, rather many important timers. Out of those, one is the advertisement interval. So as we see, right, we have essentially two kinds of pairings. One is your eBGP and other is iBGP. Normally, different vendors have different default timers to send the update. So to just give an example, let's say if I have a route, if I have a topology which is converged, and let's say there is some internal event happens, maybe your route goes or your next hop gets changed. So in this case, you have to withdraw the route first, which is the best, which is I originated, and then you have to look out for other possible routes which are present for the same prefix, right? So for iBGP, the advertisement interval is sometimes set to 0 or 5 second default. So that means as soon as I detect any kind of convergence event, I will start sending the updates immediately for iBGP. And in case of eBGP, it is from 5 to 25 seconds. Again, depend on different vendors. So normal best practice, I've seen that most of the SPs keep the BGP timers, the internal iBGP advertisement interval as 0, and for external it is up to 5 to 10 seconds.
Hi, this is Augie with Charter. Just a quick question. On Confederations, you mentioned that the sub-ASs have to be private ASs. Can you use public ASs?
That brings problem. It can, see, from the configuration side you can actually do, but from the actual deployment side you should not, because the reason is, let's say if you use publicly available AS numbers, right? So those numbers can be used by other AS which are actually the external ASs, right? So it is not recommended definitely to use public ASs for your configuration sub-ASs.
Yeah, we're making assumptions that you own them, so this is just kind of a preparation. If you have multi-AS design, then you can manage between confederations and multi-AS. So, but technically you can do it as long as you own them.
Yes, you're right. Technically you can do, but as far as I know, I think it is not recommended to have public ASs for your configuration.
Just to that point.
Okay.
In my experience, it's like 19 years already. I see confederations almost always in the case of the acquisition or merging of
yes.
and in this case the public ISs preserve.
Yeah. So
one of them, or the new one, is the external one. But if I own my AS number and I'm a legitimate owner of it, I can use it. It's a just unique identifier.
Yes.
If I'm planning the new network using confederations, yeah, better use private, because then you can have it more, right? How many public ASs you may have? You may ask for 2, maybe. And with a private, you can just be more flexible.
So you are right. I just want to elaborate more here. Is basically there are 2 scenarios, as rightly mentioned. Let's say if I have acquisition, right? In those cases, there are certain BGP tools which are available. Let's say if I'm using public ASs, right? So there's something called local AS, which is useful in scenarios where you have a migration, and there's something called remove private ASs. So if you have those tools, I think it is safe to use those. And essentially, it is very useful for acquisition kind of scenario. So I thank you all for joining me today, and I hope it is informative. Thanks.